Okay, so moving on to Unit 5 now, we're looking at rates of change of exponential growth and decay functions and the number e. So this is new to us. So e is an irrational number that has a value. And just showing correct to, let's say, the first 12 decimal places of e is 2.718, 281, 828, 459, et cetera, that it keeps going. There is no repeating numbers though, so that's what makes it an irrational number. And it's a numerical constant, right? So think of it like pi. We usually look at the value of e to be to, let's say, 1 or 2 decimal places. So we're looking at e to be 2.7 or usually like 2.72, let's say, with rounding there, right? The rate of change of an exponential function is exponential. So what I mean by that, let's investigate these points here, is if you think back to Unit 4, where we looked at sinusoidal functions, right? The derivative of a sinusoidal function was still a sinusoidal function. The derivative of sine was cos, which is a sinusoidal function. The derivative of cos was negative sine, which was still a sinusoidal repeating function, right? So here we're going to be looking at the derivative of an exponential function, and it's still going to be an exponential function. So we'll show that here. So if we're looking at exponential growth, for the exponential function f of x equals b of x, so just a review of formula for growth and decay. Here, the b value, the base value, has to be greater than 1, because again, if it's exponential growth, if you remember, your base value has to be greater than 1. So here I'm greater than 1, but I'm less than e. So what was e again? So let's just write that out here. Over to the side, e was, let's say we'll use 2.72. So what we're really saying here is that if b is between 1, greater than 1, but between, so 1 and 2.72, right? Then the derivative function is going to have a vertical compression in comparison to the original function. The derivative function is going to be a vertical compression. So for example, if I was to graph this, if you remember what exponential growth looks like. So let's say this is my x, right? This is my y. Don't really need to state the origin, but if my growth curve here, right, usually start horizontal and gets more and more vertical. So this is my original function, f of x. If my b value, so if the base is between 1 and 2.72, okay, so for example, I'm just throwing a number out there, right? If f of x was equal to 2 to the power of x, right? 2 would be between those numbers. Then the derivative of it is going to be a vertical compression. So how do I draw a vertical compression? It would still be horizontal, it's still growth, but compressed means that it's taking a little bit longer, right, to get more vertical. It's more gradual. So this would be my derivative function here. Okay, if we look at the next example, for the exponential function, again, f of x equals the base to the exponent of x, but now b, our base is going to be greater than e. So what happens then if my base is greater than e? So let's say, so anything greater than 2.72, right? Then the derivative is going to be a vertical stretch. So let's say, just as an example, right, anything bigger than 2.72. So probably whole numbers you'd pick. Let's say 3 to the power of x, it could be 5 to the power of x, it could be anything, right? The derivative will be a vertical stretch. So what does a vertical stretch look like? So let's go ahead here and still graph my original exponential growth function that we're just going to compare it to. So that's my original function, which would be one of these. The derivative function would be a vertical stretch. So again, still starting horizontal, but if it's a stretch, it's actually peaking, becoming vertical more quickly. So this would be my derivative function. Okay. So the a value in the derivative function, so when I have a derivative equation, just to point out here, the a value will be greater than 1, right? Because greater than 1 would indicate a growth. So for the exponential function, what if I had f of x exactly equaling e 2.72 to the exponent of x? Okay, what if that was my function and it's exactly equal to e? What's my derivative going to look like? So this is still exponential growth, right? Because e is equal to 2.72. So that's still greater than 1. So that's still exponential growth. So if I have my exponential growth curve, my original function, and the derivative function would be actually exactly the same if I had exactly e to the power of x. So I'm going to try to, with the tablet here, you guys on paper, just draw it exactly over top of each other. They are equal to each other. So there's our 3 different solutions with exponential growth. Now let's move on to what our 3 different solutions would be for exponential decay, and just reviewing that. Okay, so exponential decay, again, remember, is if I have a value that's less than 1 for my base, right? So whether that's a fraction or a 0 decimal as a decimal, but less than 1, just be careful, is not negative, right? Negative would be a reflection in the x-axis, but if it was a -2, the value of 2 is still greater than 1. So we're talking about something that's a fraction or a decimal. So here, one example would be, for my exponential function, f of x equals b to the power of x, where b is greater than 0, because again, it has to be greater than 0 to be exponential decay, but less than 1 over e. So let's just put this off to the side here. What is 1 over e? So 1 over e is equal to 1 divided by 2.72, and I'll give you a second. You should be trying this on your own, right? Which is roughly, we'll cut it off also at 2 decimal places, 0.37. So if my b value, if my base of my original function is between 0 and 0, so I'm between, just saying 0 and 0.37, right? Then the derivative is going to be a vertical stretch and a reflection of my function over the x-axis. So let's say, as an example here, what's between 0 and 0.37? Let's say I had my original function being 1 over 10 to the power of x, because 1 over 10 would be 0.1. So there's a fraction, or as a decimal, 0.1, it's still greater than 0, but 0.1 is less than 1 over e, less than 1 over 0.37, sorry. So for my graph, to show you that, so now I'm drawing exponential decay. Do you remember how that was drawn? I start out vertical, and then I end up, as I move left to right, more horizontal, right? So this is my original function. If my base is a value such as that, then I'm going to have a vertical stretch. So how would a vertical stretch look in terms of exponential decay? But also don't forget that I'm reflecting here, reflecting f of x, and I'm reflecting it over the x-axis. So I'm going to try my best to do this here. So reflecting this over the x-axis, let's say, would look like this. Doing my best. It should be equally spaced, right, over the x-axis. I'm not going to do. And then because it's a vertical stretch, it's going to get vertical more quickly. I'm trying to show that this is hopefully looking more vertical to you faster than the red graph. So that would be my derivative function there. So that your derivative a value, right, of your equation is going to be greater than 1, right? Greater than 1 and negative of the derivative. What if I had an exponential function f of x equaling b to the power of x, where b is now in between? I already have this value. So it's b is larger than 0.37. So b is between 0.37 and 1. Then the derivative function will be what a compression would look like, a vertical compression, and also flipped over the x-axis, a reflection over the x-axis. So let's do an example here. So let's say f of x, something bigger than 0.4. So let's say 7/10 to the power of x. So that would be 0.7. That's in between these values, right? So again, my original function here, x, y, I'm trying to make them look the same, but I'm not going to be. So my original, right, vertical going down to horizontal, f of x. Then if I had a base value of 0.7, for example, the derivative function will be a vertical compression. And again, flipped over the x-axis would look something like this, but then a compression is more gradual. It's getting vertical more gradually, so kind of something like that. Okay, that would be my derivative. More flat, not as vertical, changing into horizontal as you read it left to right. So the derivative graph is going to be a vertical compression and a reflection. We just set over the x-axis, just to summarize, but the a value of the derivative will be negative and also less than 1. So the a value here would be negative, right? That's the flipping, and less than 1. What if I had an exponential function? Oh, looks like this formula did not carry over when I opened up Word here. So for the exponential function, that's okay. We can write it in here in black. You might probably, hopefully you have it printed out on yours, right? F of x equaling 1/e to the exponent of x. So the fraction 1/e to the exponent of x, comma. The derivative function is a vertical reflection of f of x. So if I have, again, we already know 1/e, right, is 0.37. So when the original function f of x is equal to 0.37, roughly, right, to the exponent of x, the derivative is going to be a reflection, but there's going to be no stretch and no compression. So I will try my best. Again, hopefully you on paper will do a better job than me. So drawing my original decay function here and try to flip that and make it look the same. I wouldn't even probably, I would try to do yours without even looking at mine, because you'll probably do a better job. So make it look like it's not stretched. Make it look like it's not compressed. It's happening all at the exact same time. That's not too bad, right? That's not too bad. So just literally flipping it over the x-axis, right? So that would be the case if I had f of x equaling 1/e, or in other words, 1/2.72 or 0.37 to the exponent of x. So those are my 3 cases for growth, or my 3 cases for exponential decay. So now let's practice this here. For the following exponential functions, determine whether the derivative, oh, again, sorry, another mistake in this one. I don't know if you guys have that. Function f. For the following exponential functions, determine whether the derivative function is a vertical stretch or a vertical compression. So it's going to be one or the other. Can't be both there, right? But and or a vertical reflection. You can't have a vertical stretch and a reflection, or vertical compression and a reflection, or just a stretch or compression with no reflection. So if we simply look at y equals 3.5 to the exponent of x, right? So if I've got my general equation here, my b value is 3.5, which indicates growth greater than 1. So I have to go back up to my growth examples here and look up where 3.5 comes into play. So exponential growth Is that between 1 and 2.72? No. So that would be where B is greater than. So that's the second bullet, right? So I'm going to have a vertical stretch. That's all. So trying to line this up properly on here. Function. I'm going to have to keep moving back and forth. So just to write down here what we just found out, 3.5 is greater than E. So I was in the second bullet of growth. So we're talking about just a vertical stretch. So we're talking about y equals instead of f of x equals, same thing here, right? So because it says y, I'm going to say therefore y prime, the derivative of that function, of that exponential growth function, is a vertical stretch of y in comparison to y. Y prime is a vertical stretch compared to y. Okay, does that make sense? So for B, if I'm looking at 5 over 7, y equals 5 over 7 to the exponent of x, first of all, what is 5 over 7 to help us out here as a decimal is 0.7. 0.7 is less than 1. So I have exponential decay, first of all, so I know where to look. So I have exponential decay. Where does 0.7 fall in terms of those three bullets just up above? Is it between 0 and 0.37? No. Is it between 0.37 and 1? Yes, so it's also the second bullet, I'll write down. So the answer is it'd be a vertical compression and a reflection. Okay, so going back here. So we said exponential decay. So we said 0.7 was the second bullet, just pointing that out from the decay section. So that's the second bullet. So then again, because I have y here, I'll say the derivative y prime is a vertical compression. And a reflection of y. Now be careful here how I wrote this. Because it said y, right? It could have said f of x. So then this would have said, therefore, f prime of x, the derivative of f of x, is a vertical compression and a reflection of f of x, right? Meaning I'm not reflecting over the y-axis is just what I'm pointing out. It's always a reflection over the x-axis. Just be careful of that. I'm reflecting the function y, but the reflection is always over the x-axis. So here, let's take a look at decimals. Y, or f of x, equals 0.234 to the power of x. So first of all, that's greater than 0, but that's less than 1. So my b value here is 0.234, which is less than 1. So I'm just saying I have exponential decay here. So I'm looking at the three bullets just above me under exponential decay. So I'm trying to find where the decimal 0.234 falls into play there. So if I go up, again, you have stuff written here. So I'm between 0 and 0.37. Well, 0.2 is between 0 and 0.37. So that's the first bullet, which means I have a vertical stretch and a reflection. So let's write that down. So it was the first bullet I was looking at. Be careful that you're looking at, decay and not growth or decay instead of decay, depending on where you are, right? So that was the first bullet. So y prime, because it's talking about y, is a vertical stretch. And I have to flip it over the x-axis. Vertical stretch and a reflection of y. Okay. So again, y equals 6 over 5 to the power of x. So you might want to change that to a decimal. 6 over 5 is 1.2. 1.2 is greater than 1. So I actually have exponential growth. So I'm back to the first page, looking at those first three bullets there to see where 1.2 falls into play. So let's go up and see. 1.2, 1.2. So Is B between, is 1.2 between 1 and 2.72? Yeah, right. It's a little bit bigger than 1 and it is smaller than 2.72. So we're in the first bullet here of exponential growth. So let's just jot that down. And I believe, yeah, this is the last time I'll have to move stuff around, sorry. So we're here, 6/5 is 1.2, which is greater than 1. So that's what told me that I was looking at exponential growth because it was greater than 1. So it is between 1 and 2.72. So that was the first bullet. Be careful of exponential growth to go back and look at. So therefore, my derivative function is a vertical compression, what the first bullet says, of y. No reflection because it's not decay. Okay, so it's just going to be a vertical compression of the original function. So let's give these a try.